Hi. For the past 2 years, I've worked on an SRE team at Google that supports the Google Search app on Android, iOS, and Android Go, plus Google Play services, which you may know from hits such as this one. This talk is SRE for mobile applications, as a specialization of client-side SRE. You'll hear me say client-side a lot. I mostly do mean just mobile applications. My team's main focus has been on Android applications, and much of what I'm about to talk about is based on that. Today, I'm going to be talking about how the SRE principles and mindset can be applied to the client-side mobile world. Why are we applying SRE to mobile apps? What have we discovered to be the foundation of client-side SRE? I'll be talking a little about some of the problems and outages we've faced and what we've learned from those experiences. And I'm also hoping to paint some sort of a picture of what I see as the future of SRE support for mobile applications. Now, to answer why we want to do SRE for mobile, we first need to clarify what it actually means. We'll also look at some of the differences between server-side and client-side SRE. By way of example, this is a graph of crashes in the Search app from an incident we faced about 2 years ago. As an SRE team for a mobile application, we were able to detect, debug, and resolve these crashes in the same way as a server-side SRE team would handle a similar incident. Mobile SRE is much the same as server-side SRE. The problems look a little different, our focus areas change slightly, and there are a few small challenges, but we can still apply the same methodology we apply to server applications. There's this nice quote from Ben Traynor in the SRE book, but I'm not going to let you read that version. My colleague Christine produced this slightly amended version in an equivalent talk at SREcon Americas last year. An SRE team for mobile is responsible for availability, latency, performance, efficiency, and in particular, change management, monitoring, and emergency response. As a team focusing solely on client devices, we've had limited interaction with capacity planning. Change management is where we've probably done the most beneficial work, with monitoring and emergency response not far behind. For us, these 3 pillars of SRE have formed the platform supporting the other 4 points. Applying SRE to the client-side world has some useful advantages. The first is really the key reason why we do SRE for mobile. We care about the user experience, and interacting with and measuring that on the client is the most accurate way to do the best thing for our users. We can work with much more of the stack than a typical SRE team would, and deal with failures that can come from anywhere in that stack. As a result of this, we often work with many different teams from different levels, as we want to be aware of how both server-side and client-side issues affect the user. We can quantify and protect the user experience more effectively by using rich client-side metrics, which can make use of the client-side context. You can also have the client itself compute functions of metrics, such as time between events. If you did this server-side, you'd have to do some heavy lifting to match events from the same client. There are also lots of ways we can make improvements to the user experience from the client side at much lower cost than from the server side. For example, shaving 50 milliseconds off of server-side latency may require Herculean effort, and it may be unnoticeable if most of the user experience latency comes from the client side. Interacting with the client itself also gives us plenty of opportunities for managing load on back-end servers. We can experiment with smearing and traffic shaping on the client to flatten out diurnal cycles and spikes. And we can implement degraded behavior, where your client acts as a line of defense against server overload. Unfortunately, not everything is sunshine, rainbows, and unicorns. We do not control the hardware our code is running on. In a server-side world, you can change binaries and update configurations almost at will. In the mobile world, we cannot force a user to download a new binary or a new configuration. They may not have space on their device. They may have a metered data connection or no data connection at all. They may simply just be unwilling to accept the upgrade. We've seen from user feedback that many users consider upgrades to be an indication of poor quality software. They assume that all the upgrades are just to fix bugs. We're effectively asking for users' permission to change things for them whenever we do offer an upgrade, which we don't do for server updates. We have to make that change process a good experience for the user. In the server-side world, it's usually fast and relatively cheap to roll back, and you can guarantee that everything will get rolled back. This is less true on the client side. It's slow, users bear the brunt of downloading, and not every user will actually accept it. The client-side world also operates at a completely different kind of scale to the server-side world. We have far more individual devices rather than a smaller number of servers, each doing a lot more work. Losing a single server can often have no user impact, but bricking a phone will have effects for that user beyond just your app. These three things add up to one big problem. In the mobile world, we are working with a hugely heterogeneous environment. There are billions of devices and thousands of device models. You'll see every possible OS version with every possible version of your application. We also have to contend with variable and often unreliable networks, which can affect your client in many different ways. And finally, while in the server-side world, we expect fast, reliable, and accurate monitoring, in the client-side world, we have to tolerate imperfection. In part, that's because we're reliant on those devices checking in. But we also see some strange effects due to our environment, and we have to contend with difficulties that I'll come on to shortly. Going back to the original question, why do we want to do SRE for mobile applications? It is because we want to see the whole problem space, and we want to make the user experience better. So, what can we do to make things better for our users? Step one of SRE for mobile is monitoring everything we can on the client side, from performance and business metrics to just asserting that everything is working as intended. As I've mentioned, that monitoring is imperfect, but imperfect monitoring is better than no monitoring at all. Any kind of real-time client monitoring is going to work in roughly the same way. The client logs events and metrics using some API, which batches up and sends data to a server somewhere. That server then reports on behalf of the client devices. You may well be able to use any logging you're already doing to provide this monitoring by hooking into your logging pipeline server-side and, for example, exporting counts of different log messages. Come on, there we go. Real-time monitoring is not without its downsides. In our heterogeneous environment, any given metric you want to monitor will have many possible dimensions, each with many possible values. It isn't feasible to monitor every combination independently. At Google, we tend to keep a small number of key dimensions like application version and other things specific to the metric itself. We rely on other sources of data if we need to break it down further than that. This is made easier by using the same log messages sent from the client for both these cases. We have to consider the cost of this logging and monitoring, particularly in terms of battery and radio usage. This is why we want to batch up the logging. However, the result of this is that your so-called real-time monitoring isn't real-time anymore, but that's usually okay. With a large enough user base, you'll notice any catastrophic change very quickly, but more subtle changes may take a while to come across. We also have to be conscious of the reliability of this monitoring, since you're still reliant on hardware that you don't control. In particular, consider the different failure modes. What if your app gets into a state where it can't send information back to you? To guard against this, you should almost always have meta-monitoring to check the health of the monitoring pipeline itself. Another tool in your arsenal for checking up on your mobile applications is continuous integration against production. This may sound a little odd, as testing and continuous integration is usually the remit of test engineers rather than SREs. But in this case, this is testing solely for the purpose of monitoring. You may already be running black box probes. We extend this to test end-to-end by running UI tests in emulators against your production servers. This can ensure that the critical user journeys in your application are working as intended, and that your application is correctly handling what the server returns to it. If you already have UI tests running against hermetic servers or mocked responses, you may be able to reuse these for probes. An advantage of running such tests on emulators is that they're not reliant on information getting from your users back to you, as you are for logging and monitoring. However, unless you have a lot of time on your hands, you're probably not going to be writing enough of them to cover every possible thing a user could do. A final pillar of monitoring is system and app health, covering metrics like resource usage and application responsiveness. Our applications are operating in a shared environment with restricted resources, extremely restricted in many cases. And it's one of our jobs as application developers and SREs to steward our usage of these resources. On Android, if you're using the Play Store for distribution, you'll automatically get metrics for these in the Play console. There are also ways to instrument your application from within for measuring these metrics and profiling your app. A standard addendum to monitoring is SLIs and SLOs, which we commonly use to guide our work and make sure we improve the user's experience. In the server-side world, we're used to having accurate SLIs and tight SLOs, which provide a meaningful error budget. This error budget can be used to configure alerting, guide releases, and induce panic when the budget is exhausted. In the client-side world, we tend to have a higher baseline rate of normal failure, even just from things like user behavior and network problems. Because of these and other factors, we expect only around 85% of text searches in the search app on Android to be logged as successful. Our SLOs are based on this, but they aren't SLOs in the normal sense, as they're just set based on performance to give us a baseline expectation. A 15% error budget is hard to interpret and make use of. In the server-side world, we expect every request to succeed and budget for imperfection. An incident that causes only 0.05% of requests to fail may well be grounds for panic. But in the client-side world, 0.05% of actions failing may be completely indistinguishable from noise in the baseline failure rate. The other place that SLIs and SLOs fall down in the client-side world is that you're probably measuring it across your entire heterogeneous environment. Even if you have continuously improved with each new release, any improvement you make only applies if people actually upgrade. You have a long tail of old versions dragging things down. That long tail is the graph you see here. The 4 big blocks at the bottom are 4 successive releases, each of which reaches about half of the total population. The other lines at the top are the versions that account for the other half of all searches between them. We used to have a process where we'd filter out failures, such as network problems, that we deemed to be not our fault. And this actually gave us 2 or 3 nines of reliability. We also had a meaningful error budget that we could apply in a similar way to a server-side application. However, we eventually plateaued. We were no longer making any improvement to the SLI. All of the improvements we could make were instead impacting those errors we considered not our fault. Eventually, we removed the filtering in favor of raw success rate. Whenever we canary a new release or feature flag, instead of looking at absolute numbers, we compute the relative change between the treatment group and an equivalent control population. The noise from baseline failures and our diverse populations means it's almost impossible to draw any kind of absolute line to evaluate against. Instead, we define a threshold for acceptable measured regression between control and treatment. We cannot simply outright reject any change which causes a regression. Even with computed confidence intervals, we still have some amount of noise, and we have to allow potential small regressions. Similarly, there are occasions where we'll accept a small regression in one metric if we have other metrics that show significant improvements. To counteract these regressions, we have teams independently working on improvements that ensure we never get into a critical state, using both real-time and long-term monitoring to guide that work. So, that's step 1, monitoring. There we go. Step 2 of SRE for mobile is release management. This includes making binary releases as close to no ops as possible to avoid the need for rollbacks. And, as is standard practice for servers, always doing progressive releases rather than rolling everything out at the same time. In the mobile world, we have to be much stricter on this by ensuring that each individual change or feature is progressively rolled out, and more specifically, rolled out in a way that it can be rolled back. No-op binary releases really just means guarding every change behind a feature flag that you can control remotely, and we only enable new code paths or behavior after the binary release is complete. The way your remote control usually works is that your application occasionally checks in after, and the server tells it what value each of the flags should have. This is very common in the server-side world, but it's especially important in the client-side world to guard against our inability to roll back binary releases. It also limits blast radius in the shared fate domain that is your application. Feature flags also allow you to separate the cadence of feature and binary releases. When it comes to rolling out your flags, you'll almost always be dealing with multiple flags simultaneously. You'll need to randomize the distribution of your flags so that when you're rolling out 2 different flags to 1% of the population, it's not the same 1% for both. One way to achieve this is by joining some stable user ID with a flag-specific seed, hashing it, and taking some modulus to produce equally sized population buckets that we can roll out to. Different seeds will produce different hashes, and so the members of any bucket for one seed should be evenly distributed across the buckets for any other seed. Unfortunately, feature flags do have problems. In a perfect world, users would not see any difference in your app after an upgrade, and your metrics and monitoring would show no changes. Unfortunately, we don't live in a perfect world, and we can't flag guard absolutely everything. For example, changes to the core of your app and large refactorings may well be insufficiently isolated to guard behind a flag. You'll need to be monitoring which flags are active so that you can identify which flag was responsible if something goes awry. But this leads to an explosion in the cardinality of your metrics by however many different combinations of feature flags there are. Given only 10 Boolean flags, that's 1,000 possible combinations. We don't have a good solution to this, especially for real-time monitoring. That cardinality also makes it difficult to attribute errors or failures. In my team, we unfortunately rely on looking at the time when a change appeared in our monitoring and correlating that with changes in our feature flags. We query our logs and monitoring after the fact to confirm whether the correlated flag is actually the trigger or not, rather than starting with our logs and trying to identify the flag from them. This problem also applies to attributing individual crashes or bug reports. If the stack trace in your crash refers to newly enabled code, it's easy. But if your new code path causes crashes elsewhere, it's hard to make the connection. Flags make it hard to write useful release notes to tell users when or why they should upgrade. In theory, that user isn't going to see any change as a direct result of upgrading. Flags also complicate deadlines for a feature release, especially if that release is accompanied by press and fanfare. It's often the case that you want to time an announcement with the release, but if you wait until the flag is rolled out, some users may have discovered it beforehand, and it will be treated like a leak. If you announce and then roll out, some users will be disappointed that they don't have access to the new feature yet. It's also very easy to forget the additional delay caused by rolling out feature flags, which makes your deadlines earlier than you might expect. Doing releases properly takes time, but it's worth it for the added release safety. The big advantage of feature flags is that they provide a more reliable control surface. In the server-side world, you might be able to reconfigure your load balancer to not send traffic to a misbehaving server or region until you can roll back the binary. In the mobile world, we have no such redundancy. In the mobile world, feature flags often provide the primary mitigation step in the case of an incident. While we usually want to clean up a flag after it has been launched, we sometimes don't if the flag can be used as a mitigation tool or, for cases of last resort, as a high-level kill switch for a feature. In some cases, flags mean there is no difference between mitigating and resolving an incident. Saying this, you do have to design your flag system to make this control surface work as well as possible. This usually means loading flags as soon as possible after the app starts, so that flags are available to as much of your code as possible. However, this is a trade-off for startup latency and a risk that I'll come back to later in our case studies. When it comes to rolling things out, your process should look something like this. We want to incrementally release to successively larger populations in sequence. Both the Play Store and the App Store have support for this, both in terms of disjoint population channels or tracks and for canarying on subsets of populations. Once your binary has rolled out, you need to roll out those individual features and changes you carefully guarded behind flags. The smaller populations here usually won't provide very useful metrics for releases. They're more intended to detect potentially catastrophic or embarrassing failure and incorrect behavior. They're a good place to pick up crash reports and stabilize the app before releasing to production. As you move on to larger populations, you'll be able to measure changes quantitatively and catch performance and quality regressions. The main purpose of the incremental binary rollouts is to guard against any changes that couldn't be or weren't guarded by flags, and to mitigate risk by limiting the blast radius of any issues. We also want to mitigate that risk for flag rollouts, so you should also incrementally roll out your flag to successively larger populations. Depending on your infrastructure, you may be able to do something like this, where you can roll out your flags in each channel after the binary has been rolled out to that channel. Again, I want to emphasize the point you should be doing this after the binary release, not before or during. Otherwise, your binary won't be a no-op anymore, and you'll be tainting whatever metrics and monitoring you're using to validate your binary. On our team, we're typically only using metric-based releases for canaries pre-production. We're usually OK with things ramping up in alpha and beta. Ramping up your flags in this way also gives you a bit of a head start for fixing bugs. If you're lucky, you'll be able to cherry-pick fixes into beta or canary, but unfortunately, you do sometimes need to go all the way back to the start. So, how do we SRE a mobile app? Monitoring things from the client is super important. It's the only way you can see the whole picture of user experience. And because reacting to issues is more difficult with mobile applications, we have to focus on release safety much more, and flag guarding is a core part of that. Moving on, let's go through some case studies of some of the issues, incidents, and outages we've faced, and what we've learned from them. Karl Landsteiner discovered the existence of the 4 different blood types. On the 14th of June, 2016, it was Karl's 148th birthday, and at midnight in each time zone around the world, this Doodle was enabled in respective countries. This graph, which we saw earlier, is crashes in the Google search app on Android. The crash rate spiked every hour on the hour as the Doodle was released to a new set of countries. In total, we saw tens of millions of crashes across millions of users. The root cause of this incident was a blank field in the configuration of the Doodle. When the search app displays a Doodle, it alters the background color of the surrounding page to match. The app crashed when it tried to pass an empty string into a color object. The fix for this incident was just to add a color to that field. As you can see from the right-hand side of that graph, as soon as the new configuration for the Doodle was live, the crashes stopped immediately, as the crash only occurred as the app was passing the config it had just received from the server. You can also see that after each spike on the hour, the crash rate tailed off slowly. Our standing hypothesis for this is that users stopped using the app because it kept crashing. In the course of resolving this incident, 3 different configuration push mechanisms were rolled back or paused, each to no avail. Some of these were because we hadn't yet identified what was crashing, but even after we identified the issue as Doodle-related, our team didn't know the mechanism by which Doodles were served. Especially in the mobile world, it's important to know how configurations get to your devices. The root cause of this incident could have been avoided if the Doodle configuration had been properly validated. There actually was an error message in the configuration shown for the blank field, but the launch was allowed to proceed without fixing it. And finally, we could also have avoided such a dramatic incident if this minor problem hadn't been allowed to crash the app at all. The app could have just used some default background color, or just failed to display the Doodle completely. This gentleman is Chandra Bose, who worked in biophysics and telecommunication. On the 30th of November, 2016, it was his 158th birthday. Oh no. There we go. What would you do? It happened again. The first time round, we were paid just after the Doodle had launched in Australia. This time, it had reached Japan as well. The reason we effectively got paid later was that a fix had been added on the client side, which greatly reduced the number of crashes. We still saw some crashes because there were still devices in the wild which hadn't upgraded to have that fix. Of course, the server-side fix of validating the configurations hadn't been done at all. A client-side fix had been released, but it clearly wasn't sufficient to avoid the problem. We still saw about 1 million crashes across hundreds of thousands of users. We have to be conscious of the fact that client-side fixes will not reach every user. If a server-side fix is possible, it's the better choice. The best choice, of course, is to do both. A side effect of this incident was that our monitoring of search reliability was incorrect. The crashes occurred just as the search results page was loaded, and in some cases, the application logged a successful search just before it crashed, even though the user only had a split second to see the results. There's no perfect way to guard against this. A lot depends on how your app behaves. but you may find you need to adjust metrics after an incident based on subsidiary information. In cases like this one, experience counts for a lot. Our on-callers recognized the shape of the crash rate and concluded that it was a Doodle-related problem. They also knew exactly how to mitigate the problem. Because of this, the time from page to mitigation was only an hour and a half, instead of nearly 4 hours the previous time. It's important to proactively generate experience for your team through practical training, such as Wheels of Misfortune and project work, in addition to postmortem and outage reviews. And lastly, when you write a postmortem and create action items, it's important to follow up on them. Adding a server-side fix for the problem was an action item in the original postmortem, but it never got done. Thankfully, it was done soon after this incident, and we haven't seen any Doodle-related problems since. In many cases, we're reliant on our developer organizations to complete action items like these. SRE engagement with a service can only really be successful if we have leadership buy-in from developers to drive work like this. In the previous 2 incidents, the broken configuration wasn't cached at all, and as soon as we started serving a good configuration, the crashes stopped completely. The graphs you see here show the crash rate in the Android search app since late October 2017. We pushed a bad configuration file to users that caused the app to crash. This config was cached, and the app crashed at startup when it loaded the configuration from the cache. More importantly, the app crashed before it could request a new version of the configuration. Those crashes have tailed off in the last 10 months, but we never fixed this. Our overall crash rate is still around double what it was before this incident. The green line here is based on the users willingly sending feedback when the Google has stopped dialog appears. You can see that it dips more sharply compared to the red line, which is automatic reporting. We think this is due to users just getting bored of the extra taps required to send feedback to us. Only 5 old versions of the application were susceptible to this problem. The configuration was pushed to a specific version and higher, and a fix had been introduced 5 versions later. But still, millions of users had those 5 versions installed and downloaded the bad configuration. The crash rate was especially high because the search app can restart without user interaction, sending it into an endless loop of crashing. We had no way to fix things for the affected users. We discovered the root cause and reverted the configuration change within 2 hours, but by that time, the damage had been done. We explored all manner of options to make things better. The best options turned out to be sending emails and on-device notifications to affected users, asking them to clear the application data. Caching configuration is often necessary, but it's also risky. If your app loads the configuration on the critical path to updating it, you may never be able to update it again. I've already mentioned that loading flags early in startup is important, but given this has the potential to make the device unable to fetch new flag values, you may want to consider implementing ways for the client to recover automatically. Because it takes clients some amount of time to update, mitigating quickly is important to prevent clients from getting into a bad state, even if the ones already in the bad state won't recover themselves. In this incident, we had 2 teams of 6 SREs spending a good proportion of their time over multiple weeks working on this incident. To clarify, that was working on solutions and fixes. The debugging step was over. This was a colossal amount of engineering time, and we ended up with very little to show for it. In the mobile world, because of our lack of control, we sometimes have to accept that things can't be fixed or even improved. The cost of any further effort far outweighs the reward gained. We can't just ignore the fact that devices with old versions of our applications exist. Shortly before this incident, we'd been considering filtering out older versions from our monitoring to avoid noise. We abandoned that. We decided we would not have accepted not knowing about these crashes. Of course, our biggest failure here was that we did not canary this configuration change. If we had, the impact could have been about 1,000 times smaller, if not even smaller than that, depending on when we actually detected the increase in crashes. In the aftermath of the previous incident, we implemented a change to ensure we finished processing new configurations before we cached them. The theory was we'd avoid crash looping by crashing before the config was cached, not after. Once the on-callers fixed the served configuration, the device would be able to pick it up. Unfortunately, the way we implemented this caused the app to go into deadlock, causing application not responding events, or ANRs. We detected this when some of our probes started failing because they, too, went into deadlock. The top graph there shows these failures. The bottom graph shows the rate of ANRs over the surrounding days. We mitigated the issue within a few hours of detecting it by flipping a feature flag. That's the end of the tallest spike in the bottom graph. Because our clients are set to obtain new flags only every 4 hours while they have a network connection, it took much longer for the rate of ANRs to decrease back to normal levels. The feature flag in question was actually rolled out to 100% of production 3 days before this incident started. The trigger for the incident was a change to a different config, which hadn't been changed during the course of the rollout. We must remember that the fixes we make are changes, and we must take care when rolling them out to users. It's important to make sure that code paths being changed are exercised during the course of a rollout, else your slow rollout doesn't prove anything. In this case, the root cause of the incident was not the trigger. We rolled back the config change that triggered the problem, which meant more config changes, which meant more ANRs. Sometimes, knowing the trigger of an incident isn't sufficient to know how to mitigate or resolve the incident. There's a few more outages I'd like to mention in passing. We've had one case of a Google Play Services release causing lots of Google apps to fail to start. We only found out about this from user feedback on our support forums. We've had 2 relatively major incidents during the course of a binary release where the release was blocked for a couple of weeks each time while we searched for a fix for a metric regression. And on one occasion, we accidentally pushed the new version of the search app straight to production without canarying. This resulted in us removing the app from the Play Store as a mitigation step. We nearly did this a second time, but caught it just in time. I've mentioned imperfect monitoring repeatedly. When it's insufficient, plain old user feedback is important, despite how noisy it can be. If you don't have a mechanism for receiving feedback from users, you may end up reliant on Twittermon or RedditMon. We had no telemetry telling us about the Play Services outage, and we would have missed it if it weren't for the user feedback. In the release incidents, we ended up abandoning a release completely to avoid delaying later releases further. While we actually saw these incidents as a demonstration of our processes working as intended, abandoning a release is a trade-off between your release velocity and the risk of any one release. You now have more changes between the next release and the baseline. I'm sure we all know that automation is way better than humans. We launched straight to production because we relied on humans to perform large parts of our release process, without automation to even verify that the humans were doing the right thing. And finally, in the release incidents in particular, we really learned the importance of communication. We had vast numbers of engineers from our developer organization working on potential issues and fixes. What I want you to take away from these case studies is this. There are differences between servers and clients, and we have to pay attention to them. We have to defend against issues in multiple ways, both server-side and client-side. And we have to be more cautious about changes due to our lack of control. So, where do I think SRE for mobile is going? My team is still the only SRE team at Google explicitly supporting mobile applications, but that's only 3 applications out of more than 150. Our main focus at the moment is understanding and standardizing on a consistent production environment and providing common tooling, frameworks, and best practices to support client applications. Unsurprisingly, one of the things we're working on is monitoring, feedback, and testing, with the goal of making it more reliable and improving the feedback loop. In particular, we want to improve the mean time to resolution of any detected metric anomalies, and we want more insight into client-side behavior. We're also working on standardizing on best practices for how apps should do binary and feature releases, and how to verify those releases. We're improving the control surface and trying to move towards a common platform for application developers and SREs to control their app remotely. In terms of what we're expecting to see outside of Google, I can only speak for Android, unfortunately. At I/O this year, Google announced additional testing tracks in the Play Store, which provide a mechanism for testing individual features or changes in isolation from each other, without those changes actually going to one of the default testing tracks or to production. We also have dynamic apps coming, which presents new challenges about how different variants and collections of features will interact. It's also another addition to our lovely cardinality problem. And finally, we have a big focus on system and platform health, in particular, battery usage and data usage. This is about as close to capacity management as mobile SREs get. The Android OS is focusing on this a lot, and the Play Store is putting it front and center for releases. Longer term, there are still some challenges we have yet to find a good answer for. Our monitoring in a high cardinality world is still not what I'd call satisfactory. My general feeling is that we need some sort of middle ground between our low latency, low cardinality monitoring and our high latency bulk data analysis. In particular, if the real-time monitoring can't detect a small regression in one particular dimension, chances are nobody will be looking for it in the bulk data analysis. We also want a better and more consistent way to handle failures that aren't our fault, like network failures, weird user behavior, crashes caused by external factors. So far, we've worked out that neither filtering them out completely nor lumping them in with other failures really works. To wrap up, if there's one key point I want you to take away from this talk in terms of an actionable thing you can do to protect your mobile applications, it's this. Thank you.
Thank you very much. Thank you very much, Samuel. We do have a couple minutes, time for one question.
Thank you for this talk. You surprised me a bit when you talked about the feature flags, that you roll out multiple flags in one release. So can you explain me a bit on scale, like how many flags are there in total, and why not one-to-one, one by one?
This is something that gives me nightmares. So in the Android Google Search app, we have a couple of hundred developers working on the application. And at any one time, there are probably 50 or 100 active flag launches progressing through the stages. The fact of the matter is, if we made it so that only one flag could be released at a time, the developer velocity would be close to zero. There are simply too many changes that people are releasing. And so we do set it up so that those flag launches should not impact each other. And so we get independent metrics for each of them and can roll back each flag independently. But yeah, it is a really big challenge.